like, extra people, and they basically just bring it to you as fast as possible. This company was created almost 5 years ago, or slightly over 5 years ago right now. And the company was basically new to this space. It wasn't alone there as well. There were other companies like Gorillas, for example, who don't exist anymore. And our founders decided that our advantage will be data. The company will be data-driven. So right from the start, it was very important that we created a proper data platform, something that can help to get to insight what is actually going on inside the company, so we know how to optimize all the processes for the company. To build this data platform, there is a team formed, the data platform team. There are 7, 8 of us right now. Actually, we are looking for more as well. This is only a data platform team. So basically, we are responsible only for building tools and processes for other people to work with data. But there are much more people working with data at Flink. We have analysts, we have data scientists. So all those people are using our platform. Currently, if you are interested, we are looking for a few people in analytics, actually 2 of them, and 1 is for a manager for my team. So if anyone's interested, I'll be happy to share more information about this one. And now about the data platform. So basically, first of all, let's agree what is a data platform. I just found, I'm in this space for a few years already, and I talked to some people. I listen a lot to videos about it, and everyone has different definition of data platform. So I picked 2 of them. IBM definition is well known, Microsoft definition as well. What they agree on is that it is a technological solution. It enables people to work with data, and it is both hardware and software. It's not a simple one component. You cannot have just data brick or Snowflake slapped into your system and say you have a data platform. It is much more than that. Often when we are talking about the data platform, we are also talking about the data engineering lifecycle. So basically this defines how data engineers see the data, how it's generated, ingested, stored in their system, transformed, and then served to our clients. And in many cases, when we are talking about the data platform, I've seen a discussion as an exercise of system design. So basically, people take this and then keep slapping products at it. So, we put some kind of data warehouse into storage, and something into transformation and ingestion and so on and so on. And at some point, there is tons of icons, and you've probably seen all those slides with millions of products inside this data space. So I decided to do something else, and I decided that I will approach this more like a product, because we are building data platform for people. They need to use it, so for them, this is a set of solutions they can use. Now, question is data platform just a cost? Because in many cases, when we are talking about any kind of platform, it's not generating money, it eats money, like infrastructure costs, data processing costs, data storage costs, everything costs. So what is the value and how to go into this? So basically get the data and deliver something of value to the team. So the value of data platform is automation of data processing. Every company can start generating reports that allow our management to take make informed decision. But data platform allows to do it easy, cheaply, and automate everything to speed up delivery, to increase the trust in the data. So that's the biggest value. It gives data to our management so they can, based on this, make better decisions. Now, if we go back to this ingestion, storage, serving part, this is the map of Flink's data platform. So we have separated it into several components, as you can see. And I will be going through those components, how they work, but this is more or less how they are interconnected. So on the ingestion side, we have data ingestion pipelines, which are working on batch data. And this is something that takes data from external or internal systems, drives it into our infrastructure for data storage. Then we have data streaming platform, which is doing the same for events and messages generated by software that we are using. So anything that is streaming goes into our data streaming platform. Then we manage infrastructure that stores the data, transforms the data, and serves the data. We have two ways to transform the data. We are using analytical engine, which is basically what our analysts see. That's the way they interact with data. And we have a very small right now. We have exactly one use case for data streaming engine. So it's just starting. Maybe in future we will have more real-time solutions or problems to solve. But right now, most of it is just analytical loads. And then at the end, once the data is processed, it's served to our clients. So it could generate dashboards, it could generate reports to be sent to our partners. It could be fed into our machine learning platform. So that's basically the very high level view of this entire data platform. Now, is this data platform big? It's hard to define what's big these days, to be honest. We have over 1,200 DBT models, like SQL files, that are processed daily in analytical engine. We have, I think, 150, 170 terabytes of data stored in our data sets. The biggest table I've seen today was, I think, 31 terabytes. And this is something that is basically tracking everything that users are doing in our application, so it's growing constantly. So we have a lot of data, and therefore we need also something to process everything. So first thing that we decided, like when we were building this data platform, first thing we had to do is just set up the infrastructure. Goals and requirements for this part, the infrastructure, was first of all to have IaaC solutions, so infrastructure as a code. Why? Because it documents your code, it defines the processes of adding new things to the infrastructure, deleting. It helps also with security, so you know who can modify the infrastructure. You can apply different processes to it, like, for example, labeling, so you can then monitor the costs of the infrastructure. And then the requirement was also that we wanted to have production, staging, and development environments. So the way we did it is with a set of different technologies, but the most important is we decided to go with Google Cloud. So everything here is working on Google Cloud. We are using a lot of Google Cloud services, but not only. The biggest decision that we made at the beginning was this. So what will be our engine to process the data? So BigQuery was the first one. We will be using also cloud storage. And then there were some other services that kind of grew around it. And once we had it, then the design and implementation looks more or less like this. We have a single repository for Terraform code that's simple and allows us, for example, to design CI/CD for both testing and for deployment. So we can verify that the infrastructure is set up correctly. We can define different projects, different environments, and then we can have people responsible for this. So we have data platform people who are reviewing this code. Every time we want to apply new change, there are always two people involved, author and reviewer. So we have the chain of responsibility. This allows us also to monitor the services, costs of the services. We are using GCP billing services, but we also have a Looker dashboard built to monitor. After all, we have data platform, we have analysts, they created a Looker for us. And then we are reviewing it monthly because costs need to be constantly monitored. Data platform can very quickly grow, and then it eats a lot of cache. So we need to monitor what's going on. And also, all access rights in resources are defined in the code, so it's never applied manually. We always know who applied this access right, for whom, in which PR, who reviewed it, so we have kind of audit as well for this. And that's basically everything about infrastructure. Once we had infrastructure, then we have the most important part is data ingestion, because we need to get the data, and then analytical engine, because people need to work with this. So first was data ingestion pipelines. Data ingestion pipelines are kind of easy and hard. On one hand, it's a very simple pattern. Everyone knows about ETLs, ELTs, like it's basics for data engineers. So it's kind of like a solved problem, but it's not exactly. The problem are data sources. Every data source is different. Some of them are available on incremental, or they are only full download, or they require you to create reports, or just export CSV files. You know, you never know what will happen. So building something that could be easy to use was very hard, and we are not really 100% there yet. What we did, the goals of this was to be able to extract data from both internal and external sources, to store it in our data warehouse, which is BigQuery, allow for fast implementations, because we want to not be a blocker for people. If they come to us, we need new data source, we want to implement it relatively quickly. And then we need monitoring and alerting on this. Technologies used. We need orchestrator. This is super important. There needs to be something that is running everything every hour, every 2 hours. So we chose Apache Airflow for this. In some places, we decided to use some solutions that are right out of the box available, like Fivetran. Segment is something that you basically need pretty much for tracking your application and users. And then there are small tools like, for example, Meltano, which is open source tool, which allows you to create. There is a DLT right now, data load tool. There are some other solutions as well, Airbytes, I think. Other than that, we also decided that we will be using Python and SQL for this. And then data is stored in cloud storage in BigQuery. And sometimes also to move data, we are using a data stream product. For alerting, we are using Slack because we all are already there. So it's nice that it sends us alerts. So how it was designed and implemented. First of all, we have one single repository for our Airflow DAX. This helps us to get better quality of code, tests, and make sure that if we, for example, produce a code for custom alerts, it will be available for all the DAX without copy-pasting data. Then we also have a repository for BigQuery table schemas, because if you load data into BigQuery, you need a schema. So we needed a repository for this. And again, this was done because we can set tests to verify that schema is properly written, so there are no errors before deployment, that it's documented, so it tells what is the table, how it should be partitioned, for example, and other similar metadata information. So that's why it's a separate repository. And then we also decided to create a repository for custom ETL components. So basically, we have a repository where we can create extractors for different data sources. And we have a framework that has a common code for extractor, And then you can define that for this endpoint, you will use this code for extraction of the data. So this way, it allows us to relatively quickly develop new pipelines by just adding custom code needed for specific data source. What else? DAG generators. This is very important if you want to make it to work quickly with those data pipelines. You cannot write DAG every time you are creating new pipeline. So what we did was write a Python code that is reading configuration file, and based on this configuration file, it's creating new pipeline. It says, what is the data source? What is the extractor to be used? What is the table name? What is the destination? All this, what is schedule. So basically right now, for most of the cases, we just write custom extractor, maybe custom transformer sometimes, and then we add a new configuration for DAG generator, and voila, it goes. And then the pipelines are basically defined in YAML. This approach, hopefully in near future, will allow us to use more self-serve. It's hard to do it, hard to ask users who are not actively developing stuff in Python to do it, but maybe with vibe coding agents and proper configuration and this kind of framework approach, we can speed up the development even faster. We already had some users from marketing team, for example, creating extractors for themselves with us only reviewing the code. It still needed a bit of work, but it's getting better. Monitoring and alerting. This is super important when you have a lot of data coming every day, every few hours. So Airflow is doing the heavy work of running it all. And whenever there is a problem, it just sends us an alert on Slack, and we can create also redirect it to, for example, to stakeholders. So they know instantly that the pipeline that delivers the data for them failed, and then we can just approach them and ask them, for example, can you check if this PayPal report was actually generated, because it's a missing file and we cannot do anything about it. What else? We are still using external services like Fivetran. We are using the data stream, but Fivetran, for example, is pay as you go, and it actually can be very costly. So we are trying to limit it, but gives us speed of delivery. Sometimes it's faster to deliver the data quickly than to deliver it cheaply. So it's still, we are looking if it is possible to do it sometimes. Now, we have really ingested data from a lot of different data sources. This amount, of course, those are only external services that we are using, and every few weeks we are adding another data source. We have right now, I think, over 20 different data sources in our library. Next one, another part of ingestion is data streaming platform. And this was interesting because we don't have many data streaming sources. Actually, we had only one data streaming source at the very beginning, which was our main application for managing all the orders. But other than that, what we saw is the need to help people manage streaming in general. Because every team is generating events, messages, then there are microservices they need to communicate. They were creating different pub-subs and then trying to use them. So what we offered as a specialist for data, that we will prepare for them a solution that will be a single message bus for the entire company. And then in this one place, they will all be able to define schemas for events and messages, create artifacts for their software, so protobuf, code for Go, TypeScript, Python, Java, Kotlin, and this list grows. And then we can manage access control and make it self-serve. We didn't want to check every review, we didn't want to be, again, it's just a service, so they should be able to use it. Things that we used, Terraform, we used PubSub. This was decision made, I have no idea why exactly. We didn't want to use Kafka because it costed a lot and we didn't have any kind of real-time data processing scenarios. So because of this, PubSub was basically much cheaper, and that's it. And it's a built-in GCP, so it's easy to use. Then we used protobuf for different languages. And the design and implementation looks like this. So we have a repository that has streams definition. And then each stream is defined as a YAML. It says what is the name of the PubSub, what is BigQuery dataset or table that will be used to save the data, if they want to save the data, who can access it, who is subscriber, who is publisher. And then we create protobuf definition because we need schema for every single PubSub topic. And then once we have it, we also can apply data governance rules. For example, field names definitions. Every single schema, every single field need to have proper documentation, because otherwise we will start losing the sight on what's going on there. So they need to provide the descriptions if they want to create a new data stream. So this helps us to keep quality of this platform. And then artifacts are generated automatically by CI/CD and available in our artifact repository. Infrastructure deployment is using currently Terraform CDK. Unfortunately, Terraform recently decided that they will no longer support CDK. So we will be thinking what to do with this. This is discussion for later. It's not the biggest problem at the moment. So it will probably stay this way for a foreseeable future. Example of this is an example definition of the service. You can see, I'm sorry it's small, but basically what I wanted to point out is everything is YAML. So you define the name of this, you define how monitoring is done, who is publisher, what are the subscriptions, there are parameters for subscription, and then you define a second file which has schema. Schema just has for every field it needs documentation. And this is what developers are providing. It's easy to check, easy to read, and based on this, our CI/CD is creating PubSub, creating subscriptions. If user asked, this data will be also saved into BigQuery. So we will, based on this schema, create a table in BigQuery. And then, in addition to this, we are also integrating it with Datadog Incident.io. So it's automatically monitored, and whenever it is causing any problems, Incident.io will ping developers who are owning this. So that's how it works. Analytical engine. This is the thing that I like the most. I was closer to developing this one. So analytical engine is how our analysts are interacting with data. The goal from the start was create medallion architecture. Probably everyone knows here what it is. This is layered approach to data quality. We call it not bronze, silver, and gold. We call it raw, curated, and then reporting. But that's just naming. Then we also started at some point to decentralize data team. So it was a requirement that we will use data mesh architecture, which means that we have separated teams who are responsible for creating data products. Then it should be self-serve, so data platform should not be involved in any part of, working with data models. Just analysts. We are just helping them. We are not checking their code, for example. And then they need to be able to define scheduling, monitoring, and alerting per each model if they need. So what we did, we used the DBT, great product really, and Airflow. We used also BigQuery because it's a driver and storage for everything. And then Docker and Slack because Docker helps us pack this dbt into small container, which is then able to run locally or in the network. And Slack is used for monitoring and alerting, or rather for alerting. The design and implementation, the most important parts. One dbt repository for all analysts, regardless of which data units they belong to. Then we have separate folders for each data unit, but they still can reference each other. So we don't need to kind of import projects for different data units. Then data governance rules are defined and checked in CI/CD in this one repository. So we can check if fields have descriptions, if fields are named properly. Basically, there are a lot of checks. I don't really remember all of them. We are using dbt expectations, for example, for some tests. And then the way it works is that we, or rather analysts, can define schedules. And then a schedule is how the dbt model is run. So we can tag models with specific schedule and say they should be run on this one schedule every 2 hours, every 3 hours. And what we have is a generator, so a Python code, which is mapping dbt dependencies models that are in the same schedule, and then they are creating out of this a file that is configuration for Airflow. So basically to create Airflow DAG. And then developer experience, so our analyst experience is enhanced by some extra tools, like for example, dev container. They have highly configurable environments, so they can define what kind of schedules they are using, how models are, like who owns a model, what tier level it is. There are a lot of like tweaks they can do. And we also, one of our analysts, actually he's currently staff level analyst, he created a package that he names OhmyDbt, which is a set of tools. Some of them are AI driven to help analysts develop the models faster. So for example, describe the models, like create a config file with metadata faster. They don't need to do everything manually. How it looks like. So this is just a output of this dbt generator, which analyzes the project, analyzes the models, and then for each schedule, it generates a set of like information, like what is the name of the DAG, what is the schedule of the DAG, how long it should last, is there any like default Slack channel for alerts, how many BigQuery slots should be used for this DAG. Then we can add owner team metadata, so we can say what is the alert Slack channel for this team, what is the access control to this DAG, where it is in our projects, in GCP projects. And then we generate model dependencies graphs. So this is the list of models, which is like nodes in the graph, and then DAG dependencies, which is definition of the edges in the graph. And then we have model manifest. So for each model in this DAG, we also store certain information, like who is the owner. So for example, who should be tagged in case this thing fails. So if a model fails, someone is informed on specific channel, which is defined there, but a tag is here. And it can be defined per model, per ownership, or per DAG itself. What is the tier level? Also, we have some tags like Airflow dataset, which allows us to use this Airflow dataset feature, which allows us to trigger one DAG after, for example, some dataset has been refreshed, some model has been refreshed. You probably, if you ever worked with dbt, you recognize it. This is a list of dependencies, those little rectangles. Greens are sources and blue are models. This is, I think, 25% of our models on this screen. So this thing, when you tag properly all the models, then it is mapped to something like this. We have a DAG that basically for each task, for each model, we are creating a separate task. And then if the model has tests, also creates a task for tests. So I know Cosmos is doing something similar from Astronomer, but we created it before Cosmos was even available. So, we never decided to migrate. Maybe we will at some point, we'll see. We are currently migrating to Astronomer in general, so this is a good solution. I could talk hours, so I'm trying to speed it up. We have limited time. Data streaming engine. This is a small thing. We just started building it. We have exactly one real-time use case, so I will not spend too much time. Because we are using PubSub, we had to use Apache Beam and Dataflow. Flink doesn't work at Flink. I'm so unhappy about it. And obviously, we have protobuf and Python code. And right now, it's a single repository for all Apache Beam jobs in configurable. We have CI/CD, which allows us to deploy different jobs from this one repository and apply similar standard to all of them. So that always was the main objective. When we have data serving, I don't know much about this part. It's fully in our data analytics. It is self-serve because we are not touching it much, but we are making sure that we have security, PII compliance, so any personal information is hidden. We have row-level security if needed. And it's single project for all curated and reporting layer data. So data mesh, we have hidden data for each team that is dirty data, and then they create data products which are available for everyone in company. And this is this curated and reporting layer. We are using Looker Studio because it's cheaper and much more approachable for people. Apache Airflow is mostly for other scenarios like reverse ETL, because sometimes we need to export this data to some other people's databases, for example, or send somewhere a report. So this is still powered by Apache Airflow and some Python code. And single repository, reverse ETL are generators. So we just add a new configuration if someone asks us, and that's it. It just renders everything automatically. And then labels in models allow us to, for example, say this column is hidden from people unless they have specific access rights to the data. And And the last one, machine learning platform. It could be a separate presentation for this one, because building machine learning platforms is we have a separate team to do it, basically, 2-people team. But the idea is that they need a framework for models to be trained, versioned properly. They need framework for serving those models, both in batch and live scenarios. And then we need online and offline feature store. So those are 3 main requirements, 3 main features of this. We are using Kserve for serving models, Feast for feature store, MLflow for artifacts and experiments registration. And then once we have a model that was trained and is served inside Kserve container, then it's running on Kubernetes, powered by Argo CD, which is making sure that all the resources are deployed properly and then ready to speed it up. And so the interesting parts of this is that we have something called champion-challenger strategy, which is basically helping us to designate specific model as a champion, best model currently, and then train new models and compare them to champions. And it's automated in such a way that if new champion is found, Then this challenger is replacing champion, and then there is a pipeline that's like deploys it to production. We have MLflow for documenting experiments and models, Feast for feature store, and then it's integrated with data streaming platform as well, because many of those requests are coming from streaming. So for example, websites are sending us requests for live in inference. And then Argo CD and Kserve for those models. I would be happy to invite here my friends from ML team. Maybe they can tell more about this one. And yeah, that's it. Thank you very much.